In this video, we are going to talk about antiderivatives and indefinite integrals. Okay, so first off, a differentiable function f is called an antiderivative of a function little f on an interval I if the derivative of cap f, capital F, equals little f for all x in the interval I. So we are not talking about taking the derivative. We are talking about a function whose derivative is the given function. So for instance, if I have this function f of x equals 3x squared, an antiderivative of that would be f of x equals x cubed, or cap f equals x cubed. Because when I take the derivative of x cubed, I get 3x squared. So in a sense, it is a reverse, right, of the derivative. Here I have a function g of x equals cosine x. An antiderivative of cosine x would be sine x, right? Because the derivative of sine x is cosine x. So again, we are going backwards. This is one that sometimes confuses people because you, at this point in the class, are used to dealing with derivatives, right? And the derivative of cosine is minus sine x, okay? But that's not what we're talking about here. We are talking about a function whose derivative is cosine, and that function would be sine. So, or one of those functions would be sine. So we say that sine x is an antiderivative of cosine x. Let's say we had the function secant x times tan x, right? And we want to find an antiderivative of that. It would be secant x, right? Would be one of the antiderivatives. Because the derivative of secant x is secant x times tan x, okay? So again, sort of the reverse of the derivative, and so again, that makes sense why they call it the antiderivative. All right, one thing to get used to is that antiderivatives are not unique. In fact, if you have one antiderivative, it's pretty easy to find infinitely many antiderivatives. And that is not the case with derivatives, right? If the derivative of a function exists, then it is unique. So going backwards, right, antiderivatives are not unique. So we've already talked about one antiderivative of 3x squared is x cubed. Okay, well, so is x cubed plus 1, an antiderivative of 3x squared, right? Because when I take the derivative of this using the sum rule, I'm going to get 3x squared plus 0, right? And because the derivative of any constant by itself is 0, so I'm going to wind up again with 3x squared. And so you can see that x cubed plus 2, for the same reasons, right, would be an antiderivative of 3x squared. X cubed plus 9/5, also an antiderivative of 3x squared. X cubed plus 3 times pi is also an antiderivative of 3x squared, right? Because the derivative of x cubed would be 3x squared, and then plus the derivative of 3 pi. Since pi is a constant, 3 pi is a constant, and therefore its derivative is 0. So you would again just get 3x squared. Okay. All right. And so you can see it's not too hard. All I need to do is to find x cubed and put a constant on, plus a constant on x cubed, and I will come up with a different antiderivative of 3x squared. So there are infinitely many antiderivatives of a function if it has one. This theorem here tells us that for continuous functions, at least, then the antiderivatives can't be that different from one another. In the previous slide, you can see that all of these antiderivatives we looked at are kind of the same. They're x cubed plus a number. And so you might ask, well, does 3x squared have an antiderivative that looks different from that? And this theorem tells you that the answer to that question is no, right? If I have a continuous function, lowercase f or little f, and I have two antiderivatives, f and g, well, then they have to differ by a constant, okay? So that says that pretty much all of the antiderivatives for, say, 3x squared are going to be x cubed plus a constant, okay? So that's pretty much all of the antiderivatives. So next up, we introduce a new concept called the indefinite integral of a function. And what the indefinite integral of a function is the set of all antiderivatives. Okay, so that's all of them. All right, so a specific example of this, we might have this sign, which is called the integral sign, and then 3x squared. So this would be the set of all antiderivatives of the function 3x squared. And so what we just got talking about was that we would know that the set of all antiderivatives of 3x squared would be x cubed plus some constant c. So we usually just leave that uppercase letter c right here to indicate that this is the format basically of all antiderivatives. In fact, that's what that previous theorem says, right? Any antiderivative of 3x squared is going to be x cubed plus some constant c. Okay? All right. And this chapter is going to be all about finding antiderivatives of functions like this. All right, a little bit about the notation. First off, this elongated s symbol here is called the integral sign. The function that is inside the integral here is called the integrand. This dx has a couple of purposes. It tells you where the integrand ends. Okay, so maybe you have an integral involved in some other equation, so you kind of need to know where that integral ends. You could put parentheses around the integrand if there are some other parts of the expression in there. It could be confusing. This dx also tells you what's called the variable of integration. So, and you might say, well, it's obviously x because x is the only variable here, so why do you need the x here? But the thing is if you go into say Cal 3, if you have to take that class, you'll see functions in there with several variables in there, and you'll be integrating with respect to the different variables. So it becomes more important in that class because you'll know, okay, I'm integrating with respect to x, or if it was dy, then you would know the integration is with respect to y, or dz, the integration is with respect to z. So we won't really see that in here, but that's another reason why it has this variable here. Sometimes you will see constants in here, and then you'll know if it's not this variable, then it has to be a constant. The plus c that we get when we put on, when we evaluate an integral, find the antiderivative, and then put the plus c on there is called the constant of integration. Okay. All right, so next up we're going to talk about some basic integral facts, and then we are going to use these facts in the examples that I show you. So we're just going to go over all the facts, and then when I work through the examples, you'll see the facts that I'm talking about. Okay, so the first fact is that the indefinite integral of 0 is just a constant c, right? The derivative of any constant, right, would be 0. So if I had the antiderivative of 0, right, it will just be any constant. The indefinite integral of 1 would be x, right, plus some constant c, right? The derivative of any expression that looks like this, x plus a constant, the derivative will be 1, right? So that's the antiderivative. Next up, we have a very important rule, and this is called the power rule for indefinite integrals. This tells you how to find the antiderivatives, the set of all antiderivatives, or the indefinite integral, right, whatever you want to call it, of any power function except for 1. All right, so, and this is basically just the reverse of the power rule for derivatives. So the power rule says what you want to do is to find the indefinite integral of a power function is add 1 to the power, so this would be n plus 1, and then divide by that new power. And then, of course, don't forget the plus c on the end. All right? This formula only holds true if n is not equal to minus 1. If n is equal to negative 1, right, then there's a real problem right here because I'll have negative 1 plus 1, which is a 0 on the bottom. So x to the minus 1 is the only power function for which the power rule does not apply. This is an extremely important rule. Okay, so we're going to be using this quite a bit. So that one power function for which the power rule doesn't apply, x to the minus 1, if you remember, x to the minus 1 can also be written as 1 over x. So if your power function has an exponent of minus 1, you need to use this rule right here. Okay. And so that says that the indefinite integral of 1 over x is the natural log of the absolute value of x plus c. And again, that one is pretty much the reverse of a derivative rule, right? The only difference is that with the derivative rule, we had parentheses around the x. The derivative of the natural log of x equals 1 over x, right? So the reason why there's an absolute value on here is because of the fact that you get a function with a bigger domain when you do that. Let's see if I can pop out of here real quick and take a look at Desmos. Whoa. Change the site there. If I graph the natural log function, it looks like this. And the domain of the natural log function is x greater than 0. And I think I'm going to have to enter it like this. If I graph the natural log of the absolute value of x, then not only do I get this part over here on the right, I also get this part over here on the left. Okay, so this function, the natural log of the absolute value of x, has a larger domain than the regular natural log x function. And we really didn't need to talk about, we didn't really need the bigger domain when we were talking about derivatives, so we just kind of ignored the absolute value here. But now from this point on, right, when you integrate 1 over x like this, then you will need to put that absolute value on there, okay, to get the function with the bigger domain. All right, next up are the exponential functions. So the general exponential function, a to the x, remember a has to be positive and not equal to 1. Its antiderivative will be a to the x over the natural log of a plus some constant c. Okay. And then e to the x, the natural exponential function, remember it's its own derivative, right? So that's going to make it its own antiderivative as well. So that means the set of all antiderivatives, the indefinite integral, is just e to the x plus some constant c. So you can see why we use this one in calculus a lot. It just kind of gives us simpler expressions than the general one, and you can rewrite any exponential function to any other base that you like. So, all right, so one thing that we skipped over is the natural log. We didn't do that because that's actually a Cal 2, traditionally a Cal 2 problem. So skipped over that. And then these are the basic integral facts for the trig functions. You'll notice that not all of them are in here. Really, these basic integral facts are really just the reverse, right, of the derivative facts, and that's all we're really doing here. So the indefinite integral of cosine is sine, right? And the indefinite integral of sine is minus cosine x plus some constant c. Again, that's a little bit backwards to probably what you're used to, right? You may remember the derivative of cosine is minus sine and the derivative of sine is cosine, but that's not what we're asking about here, right? When we go to do the indefinite integral, what we want is a function whose derivative is cosine, and that is sine, okay? We want a function whose derivative is sine x. That's not cosine, right? Because the derivative of cosine is minus sine. But when we attach this minus out, right, and check to take the derivative here, the derivative would be minus of minus cosine, which comes out to be sine. All right, and the antiderivative of secant squared is tan x. The indefinite integral of cosecant squared x is minus cotangent x. Antiderivative of secant x tangent x is secant x. And the antiderivative of cosine x, cotangent x is minus cosecant x. So really all of these are just the reverse, right, of the differentiation rules. You can see we don't have tangent or cotangent or secant or cosecant over here on the left side. That's because that's one of the very last things that we will do in this class, because it's not a basic fact. It takes a more advanced technique called integration by substitution, and that is the last thing that we'll cover. Finally, just some basic integral facts for the inverse trigonometric functions. The integral of 1 over 1 plus x squared is tan inverse x. Integral of 1 over the square root of 1 minus x squared is the inverse sine. The integral of 1 over the absolute value of x times the square root of x squared minus 1 is secant inverse of x plus some constant c. Those are the three that are traditionally used. The reason, if you go back and look at the derivative facts for the inverse trigonometric functions, you can see that, say, like for instance, the derivative of cotan inverse is minus 1 over 1 plus x squared. So really, these are the three that are most commonly used in moving forward with this class, and then again in calculus 2. So that's why we're sticking to these. You may wonder where the other ones are, but just try to make this list as small as possible. All right, three different facts that come straight from the derivative facts, and these are facts for basic integrals, or indefinite integrals rather. So this is the constant multiple rule that says if I want to take the integral of a constant times a function, I just rewrite the constant and then take the indefinite integral of the function part. So that works exactly the same way as derivatives does, right? Which is nice. Next up is the sum rule for indefinite integrals. That says if I want to find the antiderivative of a function that is built by adding two other functions together, all I have to do is take the indefinite integral of each piece and add them together. And same thing for the difference, right? This function is made by subtracting two other functions. This rule says if I want to find the indefinite integral of that, then all I need to do is take the indefinite integral of each piece and then subtract the results. Okay, so these rules work, exactly the same way as the derivative rules work, and so that there is no mystery as to why. That's because this is exactly how the derivatives work. So when I'm going backwards, looking for a function whose derivative is a particular function, then it works exactly the same way. So these three rules are very nice. The downside, though, is that is where it ends. Okay, and this is extremely important. Okay, that you understand. There is no product rule for indefinite integrals, and there is no quotient rule for indefinite integrals. If you think back to derivatives, right, those first three rules that we talked about, the constant multiple rule, the sum rule, and the difference rule, it was right in the product rule where things started getting more complicated. Okay, so the product rule was more complicated, and the quotient rule was more complicated than the product rule, right? But the thing is if you knew how to take the derivative of each piece in a product or a quotient, then there's just one rule that told you how to do that for derivatives and one rule that told you how to do that for quotient rules. But unfortunately for indefinite integrals, because those rules are starting to get more complicated, when you're going backwards trying to find the indefinite integral, the situation is much more complicated. There's not one rule that will tell you how to take the indefinite integral of every single product or every single quotient, right? It is a collection of rules and techniques that you'll need to study. But fortunately, for us right now, that's in calculus 2, right? The main thing, right, for you to realize now is there's no easy way to do this, okay? There's no product rule or no quotient rule. And for us in calculus 1, that just means that if you have a product rule or a quotient rule, really our only technique that we'll be able to use is to, if it's a product, is to multiply it out, okay? And then try to use a different rule to take the indefinite integral. And I'll show you how to do that in the examples. And same thing for a quotient rule. If a function is a quotient, a division of two functions, then we're going to have to manipulate it so that it's not a quotient of two functions anymore, and try and just go back to these rules right here, which are easy to use. So for the problems that we look at, I'll show you exactly how to do that. If you have to go on to Calculus 2, then you need to be prepared, because you'll jump right into that in Calculus 2. All right, that's it for this video.